Good day, everyone, and thank you for joining us for today's R&D Services webinar, Best Practices for Testing Prototype Cells at NOVONIX. My name is Lori McLeod, and I'm the president of NOVONIX Battery Technology Solutions based in Nova Scotia, Canada, and I'll be your host today. Before we get started, just a quick housekeeping note. Today's session is being recorded, and we'll be sharing the link to the recording tomorrow. If you have any questions at any point, please drop them in the Q&A box at the bottom of your screen. We'll save time at the end to answer as many as we can. I'm pleased to introduce today's presenter, Dr. Andrew Van Bommel, our Cell R&D Manager here at NOVONIX. Andrew is part of our R&D Services team, where he works closely with customers on cell design and prototyping, performance testing, and advanced analysis for a wide range of battery chemistries and formats. Andrew holds a PhD in chemistry from Dalhousie University, where he studied cathode materials under Dr. Jeff Don. He also held roles with 3M Canada and Salient Energy, and now leads a team of battery scientists at NOVONIX focused on prototype cell design, testing, and analysis. In today's session, Andrew will walk through NOVONIX's best practices for testing prototype cells. He'll start with early stage coin cell testing and how those results guide cell design and development decisions. From there, he'll move into full cell assembly and evaluation, covering topics such as electrolyte filling, vacuum sealing, stack pressure, and key diagnostic measurements like AC resistance and formation gas volume. He'll also discuss formation protocols, long-term cycling, rate capability testing, DCIR mapping, and NOVONIX's Ultra-High Precision Coulometry methods. The examples included conventional NMC graphite systems, as well as more advanced chemistries, such as silicon-containing anodes and sodium-ion cells. With that, I'm happy to turn it over to Andrew.
Thanks, Lori, for that introduction. So today I'll be talking about best practices for testing prototype cells at NOVONIX. So I hope we can give some insight as to how we test cells at NOVONIX, and maybe that will give you some indication or some insight on how you will test your cells or how you will work with NOVONIX in the future. So I'll get started here. Here's an outline of today's presentation. So I'll give a brief overview of NOVONIX, the company, including specifically where we are located, NOVONIX R&D Services Group. Then I'll go into cell testing. So we're starting today with cell testing, the setup and check-in. I'll show you why we do that. Discuss some of our standard formation testing and why we do formation the way we do, what kind of metrics we get from that. I'll talk about long-term cycle testing. So that's just normal cycling, normal CV charge and CC discharge, just continuous cycling. And then also testing with NOVONIX UHPC, just showing the benefit of using NOVONIX UHPC, which we typically do in a lot of our different projects. Also another test, just rate map and how we do a destructive rate mapping. I'll talk about a few special considerations, stack pressure, voltage range, really important there. Also temperature control. Then I'll give a summary of today's presentation, and I'm happy to field any questions that you have along the way. And you could also put them in the chat, as Lori just mentioned. So NOVONIX Group consists of 3 separate divisions. So we have our NOVONIX Anode Materials division, which is making a synthetic graphite in Tennessee, USA. So this is going to be, or is, a leading domestic supplier of battery-grade synthetic graphite, and it has a large-scale operation there. And then in Canada, we have both the NOVONIX Cathode Materials division and the NOVONIX Battery Technology Solutions division. We call this BTS here. So in the Cathode Materials division, we are commercializing a patented synthesis. So this is an all-dry synthesis, as opposed to the conventional co-precipitation reaction. So this is an all-dry patented synthesis method. And you see here an image of our rotary hearth kiln where we have some pilot operations. We're able to produce up to 10 tons per annum in this pilot facility. And then we have our the Battery Technology Solutions division, BTS, 2 separate groups within that. So one is the highest precision, highest accuracy cell cyclers. So this is called UHPC, Ultra-High Precision Coulometry cell testing equipment. And this is able to give you insight as to the cell performance within a relatively short period of time, what the cell is going to be doing further down the line in its lifetime. And then where we are is the R&D services division. So we have the whole industry standard capable mixing and coating. So we do planetary dual shaft mixing. We have 2 slot die coaters. We have a dry room to do the punching and the assembly of cells and the filling. And we also have numerous people around, just the expertise to accelerate your development programs. The advantage of working with NOVONIX, we have a team, as I mentioned, of experienced battery scientists. We also have engineering team with R&D and mass production experience. As I mentioned, we have a full equipped prototyping facility, and we're able to test those either stack cells, cylindrical cells, coin cells with our over 3,000 cell cycling channels, including hundreds of UHPC testing channels. So some of the examples of engagements that we have with our customers include different work in the lithium-ion battery, but also more recently in the sodium-ion battery systems. Sometimes we look at different electrolyte formulations, different additives in those systems. Sometimes we look at different anode, different cathode, of course, conductivity enhancers. So if there's a different conductor to be added to the anode or the cathode, and also looking at other things like different separators, different current collectors, and even more. So since we have the whole facility, the cell line facility, making those prototype cells, we can introduce your material any step of the way. And the advantage of working with us is it saves on the capital expense in standing up your own prototyping facility, but we also have dedicated production staff. So day in and day out, this staff is working on making those coatings, doing those mixes. So there's a lot of experience there making the cells. We also leverage knowledge from industry professionals, whether they came from industry and working with us, or we have contacts with other industry professionals as well. In this way, you can accelerate your R&D program. We also have a project management function for every customer. This ensures the project is on track and is followed closely. We have a highly interactive engagement, so we welcome you on site, for instance, to see your project in action. And we have a flexible project scope for all of our projects with our customers. So that could include only electrode making, for example, or only cell making, or we could fill the cells, test them. We could do any and even disassemble them, do some post-mortem analysis. So very flexible project scope with each one of our customers. It's very, very custom. So a few details of the cells that were tested in the presentation I'm going to give today, just focusing mostly on cell testing. So in this case, a hand coating is usually made of both the anode and the cathode in a small scale planetary mixer. This hand coating is calendared and dried. So these hand coatings are used to punch discs so that coin cells can be made. And the specific capacity is determined from these coin cells. And then a cell build is made. So there's a cell design. We usually target N over P of 1.07 to 1.15 or 1.2, depending on what we are interested in. So 1.07 is a typical N over P. And then those anodes and cathodes are then mixed with the conductors and the binders in a larger mixer. So 2, 5, 15-liter mixers we have in our prototyping facility. And this is a standard dual shaft planetary mixer. We target a target viscosity measurement so that it can be coated on the slot die coater. And so these are coated on aluminum or copper, depending on the material, in the roll-to-roll process, single-sided, and then that electrode is flipped and the other side is coated. So our target mass loading is plus or minus 3% there. Afterwards, those electrodes are calendared. In the case of the testing that's going to be shown today, these are stacked pouch cells, so those electrodes would be punched, placed in separate carousels, and stacked between the separator with an automated stacker. And then the tabs are welded to the anode and cathode stack portions. Stack is placed in a pouch and sealed, and the cells are filled by hand. They're vacuum staged and vacuum sealed. And then I'll show the next parts of the process next. So if you want more information about the electrode coating and the mixing, there's a webinar on our YouTube channel shown here. And if you want more information about the cell assembly, there's a separate webinar there. So this is going more in depth with those different stages that are outlined here. So here's our YouTube channel at NOVONIX Battery if you want to know more information about that. And we have other videos on that channel as well. So now getting into the cell. So this is, I'm going to show one specific cell initially. So this is an NMC 811 cell. Synthetic graphite is the anode. N over P was 1.07. This is about a 1 amp hour stack cell. The electrolyte is shown here. So finally, when the cell is vacuum sealed, the first thing that we do is weigh these underwater. So we weigh them underwater. This is an analytical balance, and if you can see, there's a wire under the analytical balance, and it's weighing that cell underwater. So this initial weight will be used to determine the formation gas. So when formation is complete, there's formation gas produced in the pouch cell. This adds buoyancy to the cell, so there would be a lower weight after formation, and we can use the Archimedes principle to determine the gas volume generated. So this is a great method of determining gas volume, which we might want to compare between different cells, just showing one cell initially here. We also do AC resistance prior to testing. So the ACR is shown here prior to testing. The OCV is also measured, so it's an expected OCV. If we saw 0 volts here, we'd be 0.00 volts. We'd be concerned about the cell quality, but this is an expected OCV for the cell, an expected ACR as well, and then the underwater weight is given here. So after that check-in, the cells are placed between two plates. So these have springs with known spring constants so that we could fixture the cells to a standard stack pressure. So there's rubber pads between those plates to even out the stack pressure. And these are controlled to 10 psi for our normal NMC graphite cell, for example. So that's how the cell is checked in. So after check-in, we're on to the formation. So here I'm showing the voltage versus time for our standard formation, and then I'll explain why we do formation this way. We standardize our formation so we can compare between different cells. Even down the line, if you do another project with us, we'll still do the same standard formation so we can report gas volume generated or IRC or FCE. We can have different metrics reported so they can be compared down the line. So here's voltage versus time, the voltage profile versus time for that formation step. First, we do a 30-minute rest. So this allows temperature to stabilize. Our standard formation is at a little bit of an elevated temperature at 40 degrees. And then there's a slow or a low rate charge up to 1.5 volts. So this might not necessarily be required, but it's just to completely ensure that there's no copper dissolution while this wetting step is happening. And this wetting step really is just time and temperature, allowing for more electrolyte to penetrate all the pores of the electrodes prior to doing the first charge. So this step and the temperature allows that cell to promote wetting in the cell. And then I'm showing the first charge here as part of that voltage versus time graph. So that first charge, lithium ions move from the NMC to the graphite. And during that, we can plot the differential capacity versus dV, so dQ dV. And usually we show this portion here between 2.5 and 3 volts. So this is when you get reduction of certain species in the electrolyte. VC, EC are reduced, things like that, maybe different additives if you have different additives in your system as well. So we can look at this and see if there's consistency between cells and look at different cells to see if we see the same reduction. Sometimes this can be changed depending on the salt present as well. So we look at this for evidence of that reduction, and this is evidence of that SEI formation, that solid electrolyte interphase, and that's why this process is called formation. So some more metrics during the formation. So we do that C/20 charge and a C/20 discharge. So we have a charge capacity we give a discharge capacity. We can report, if we fold that discharge capacity over on the profile, we could see the difference between the charge and the discharge there. So that's the irreversible capacity, the IRC, 0.16 amp hour. And in this case, the FCE, the first cycle efficiency, is the ratio of the discharge capacity to the charge capacity. So these are accounting for some of the losses that occur during that formation step, whether it be from the material or from the SEI growth. So this is 85.5. So we hope this will be really high, that FCE, so we can compare that between cells. Again, we're just showing one cell just for illustrative purposes here. So after that first charge and discharge, we have a few metrics there. We can see that dQdV to see that electrolyte reduction, but we can also see the FCE. And then afterwards, an important step is shown here. So it's then charged, and then during the top of charge, there's a rest step. So this is where the cell is kept at open circuit voltage. So if the cell is made really well, and there's no parasitic reactions there's not many parasitic reactions occurring, there's just some kinetic losses and some SEI growth, we can expect that this drop in voltage at the top of charge and during the rest step, so this is 48 hours we can expect that to be minimal. So this one is 32 millivolts, and we can compare this between cells as well. So we can expect that if there's some self-discharge taking place, or if the cathode is of poor quality, or the cell isn't assembled very well, we can expect this drop to be larger. So we can make that comparison, and I'll show that this is important with all of our work, that we do things, we have replicates. So the reason why we have more cells here, so usually we test in triplicate, but with our formation procedure, we usually have more cells that are being formed because those cells are going to different testing protocols. So here are 10 cells that are tested, and we see that voltage drop during that rest step, that OCV rest step, during those 48 hours. And 9 cells all fall with the same voltage drop. So these 9 cells are excellent cells. We see one outlier cell here. So it's really important to look at this step to know, well, this cell might have some self-discharge, so we can discard the cell and not have that go to the next steps. So this is a great quality check before proceeding to the next testing, and it gives confidence in the cell build and sometimes the material quality as well. So after that important top of charge rest step to get that voltage drop, then the cells are discharged to a predetermined SOC, a predetermined voltage. This one was just discharged at 3.8 volts. So the reason it's doing this, one, it limits the cell degradation. So there's more degradation at higher states of charge. So it limits that. And then often if we are forming cells and sending them to our customers, it brings them to a safer SOC. So that would be around 30% SOC would be our standard. Then the degas would happen, and then we could ship those cells. So anywhere 30 to 50% SOC. This one's probably a little higher at 3.8 volts, or it's about 50% SOC. That's where we end our discharge, so there's no more degradation, and we can go to the next steps of testing. So before the next steps of testing, as I mentioned before, we have to weigh the cell underwater. So again, the analytical balance with the hook underneath is used to weigh that cell underwater. So we have here, as I'm indicating, that underwater weight before formation, 10.17 grams, after formation, 8.86 grams. So that difference with the density of water would be the volume of the formation gas, 1.31 mils. So this can be compared to different electrolytes, to different cathode, anode materials, just to see if there's any difference in formation gas between one sample and the next. We see ACR before and after formation. We can't 100% make this comparison because we are at a different SOC. The ACR when the cell is assembled isn't of like 100% use. But after formation, that ACR can be compared to different cells and may indicate different levels of SEI that are built up with different electrolytes, for example. And then the OCV before formation, after formation, is expected to be where we stopped it. It's a little bit higher because of some voltage drop there than the 3.8 volts, but the important thing here is after formation, the cell didn't short or didn't lose its voltage. So we know that this is a good cell ready to go to its next test steps. And before that, the cell is degassed. So degassing is just cutting open the cell and resealing it, re-vacuum sealing it, and then it's refixtured to that 10 psi level. So now after that formation step, I'll talk about long-term cycling. So here's a messy voltage profile showing voltage versus time. So much messier because each one of these is a charge and then a discharge. So it's just all pushed together in this graph here. So if we zoom upon one charge-discharge cycle here, just to go over some of our standard testing for long-term cycling, it's done at a constant rate of charge, a constant rate of discharge. So this is C/3 rate for a 1 amp hour cell. That's about a third of an amp. For this 811 cell, this is charged to 4.2 volts. After that, there is a CV step, which is a constant voltage charge step. This ensures that there's still capacity from the charge step, but we don't go over the 4.2 volts, which is important for something like NMC 811 when trying to get good lifetime from those cells. So we have that CV step until C/20 current, which is 50 milliamps for this cell. And then afterwards, we have a 5-minute rest step. So we use this following terminology here for our customers. We call this long-term or LT, long-term cycling. We do CC/CV charge, so that's C/3 control constant current charge. And then at the end of that, when it reaches the upper cutoff voltage, we have a CV step until the current reaches C/20, and then CC discharge is constant current discharge at C/3. And this continues to happen cycle over cycle. And then we report the discharge capacity for each cycle, and that gives you the graph shown here, the cycle life. So here's discharge capacity. This one's starting at 0.9 amp hour, and then ending a little below 0.8 amp hour. And then to make comparisons between different cells, or maybe a cell that was made before that could have like slightly higher capacity to start out with, we normalize that initial capacity. So this one is normalized to the start of cycling. So this would be 100% capacity at the start of cycling. And this is the typical profile that we see in long-term cycling. We don't see something that's perfectly flat. There are some losses during cycling, especially when we look, this is C/3 rate. So we're not cheating the clock or beating the clock by doing faster cycling in this case. And so we have C/3, and then we are also a little bit of an elevated temperature to allow for more degradation mechanisms to occur. So it's just a little bit higher here. So this is more of a time-based losses that would exist during the cycling. And this has 89% capacity retention at cycle 1300 for this cell chemistry. So this is very typical of the kind of profile that we'd see of discharge, normalized discharge capacity versus cycle number. This is right here. So you see an extra point every 200 cycles. So this is a checkup cycle or an RPT. So we know that this is done at a lower rate, a lower current, a slower rate than the regular cycling. So C/10 is here, C/3 is here. So we know if this widens between the RPTs and the normal cycling as cycling progresses, we know that there's a strong evidence of there's impedance space fade because and sometimes the RPTs will be relatively flat, and then the regular cycling would be much below that. So let's take a look at that. So this cycling is done at 1C rate at 25 degrees. So we get more cycles this way, but you can't compare 1,000 cycles, not necessarily can be compared to 1,000 cycles at C/3, especially if it's time-based degradation within the cycling. But we see this 1C cycling, and we notice that at the beginning, the difference between RPT and the normal C/3 cycling is 28 milliamp hour. And then as we proceed to cycle 3600, it's 47 milliamp hour. So this is strong evidence of some impedance-based fade mechanisms occurring. And we see if we look at the delta V, which I'll talk about in the next slides as well, the delta V also increases a bit at that same cycle. So at some point, we're getting some impedance-based fade, or we see evidence of impedance-based fade at this level. And this is why we choose sometimes, if we want to probe impedance-based fade more, we choose a 1C rate at room temperature at 25 degrees. If we want to just look at time-based fade, then we do C/3, maybe at an elevated temperature like 40 degrees for testing. So it's important to look at that rate and the temperature of testing. And then I was talking about delta V. So delta V is the average distance difference between the charge and discharge voltages during that cycling. So we saw one example of a cycle. So it would be the average voltage during the charge subtract the average voltage during the discharge. And this gives the delta V. What this is giving is it's a proxy of a measure of internal cell resistance, or it reflects the cell kinetics. So this magnitude, if we compare one cell to another, we have to use caution when looking at the magnitude of the delta V, because some of that delta V could be from the inherent hysteresis of the cell. So if we're looking at or of the materials. So if we're looking at a cathode material like a lithium-rich oxide, or those LMR materials, as some call them, we know that has a lot of voltage hysteresis, so it's expected that that delta V will be higher. That's not necessarily correlating to any change in the rate capability. So it's important to also look at the normalized delta V. In this way, we can see any delta V growth, and we follow this closely during cycling. So here's how to compare different cells using long-term cycling. So these are some typical methods we use to compare cells. So we have two cells here. So in black is NMC 811 and synthetic graphite only in the anode. In red is the same NMC 811 coating. So this was coated the same day. So it's just using it's punching from the same coating. The only change is here is the anode. There's a little bit change in the electrolyte and the voltage ranges because it's a silicon-containing anode. But we should focus on the change being that anode that contains silicon. So it contains this silicon-carbon material, 20% is silicon carbon, 80% is synthetic graphite in the anode. And again, these are 1 amp-hour stacked pouch cells. And these are done in triplicate. We might be seeing just two tests here, but there's 2 overlaps, and that is used. We usually do in triplicate to gain confidence in the results and conclusions. And we see here that the discharge capacity fade is higher for those cells containing silicon than those graphite-only cells, and this is expected from what we see. But the silicon-containing cells are quite excellent. It's fairly close to the cycling of that graphite-only cell. So we're seeing much improvement in these silicon-carbon based materials. When we look at the delta V, again, as I cautioned when looking at the magnitude of the delta V, as expected, since there's inherent voltage hysteresis from silicon materials, if we look at a coin cell of silicon versus that silicon carbon electrode versus lithium, we would see that voltage hysteresis is much higher than in graphite alone. So we expect that delta V to be higher in that silicon-containing material. If we look at the normalized delta V, we in fact see that that delta V rise is relatively low in those cells containing silicon-containing anodes. So those are very promising cells. Those cells containing silicon here. Now I'll talk a bit about NOVONIX UHPC. So if you want to know more in-depth information about NOVONIX UHPC, we have more videos on our YouTube channel at NOVONIX Battery, including the one shown here. So this will give you more in-depth insight into what NOVONIX UHPC is and the many ways it can be used to do your testing. I'm just going to show one of our most common standard tests that we do within NOVONIX services using NOVONIX UHPC, but it can do many more things. So here's a standard test protocol using NOVONIX UHPC. So this is very highly accurate, highly precise measurements. And I'll show you what insight it could give. So within a relatively short period of time doing that testing. So here's the voltage versus time for a standard UHPC test. This is C over 10 rate, so about 10 hours for charge, 10 hours for discharge, and this is done about 25 times. And so we have a charge discharge about 25 times, a little slower rate, still at a bit elevated temperature, 40 degrees would be our standard. So when we look at cycle 5 and we have that charge and discharge, if we fold it over itself, at first, when we look at it, it looks like that discharge is the same length as the charge, and we have 100% efficiency. If we zoom into this area, we see that it's not completely efficient, that there is a difference between that discharge and the charge. So that fifth charge capacity is 0.9082 amp hour. That fifth discharge capacity is 0.90060 amp hour. And then that coulombic efficiency, so that's the ratio of that discharge to the charge, is 99.76%, so not quite 100%. So herein lies where we need that accuracy and precision, where a NOVONIX UHPC is helpful. So there's a few reasons why this gap can exist. One could be that the charge keeps on moving to the right. So there's more oxidative processes that happen during that charge process. And another could be some degradation leading to the loss in discharge capacity. So I'm going to just separate those out right away rather than showing coulombic efficiency graphs, which is what we normally do. You can check some of the videos and it'll be discussed in a different way as well. So here we're zeroing the start of the discharge curve, and we see that each discharge just gets smaller and smaller. So at the beginning, that if we zoom into that area, the first discharge is a little bit above 0.91 amp hour for the cell. And then at the end, it's below 0.89 amp hour. And the fade rate is the difference between that discharge capacity and the next one. So this would be N and then N plus 1. So that would be the discharge capacity fade. So some typical methods or some typical reasons why we have discharge capacity fade is lithium inventory loss and sometimes active material loss as well. Here's a different way of plotting that graph. So it's starting at the start of test, we were at 3.8 volts. So there's charge of that. After this step, there's the charge at C over 20 and the discharge. So this completes 25 times. And we could see that that charge endpoint is walking along. And this is because there's some oxidative processes that are causing this charge endpoint to walk along. And the difference between one endpoint and the next is the charge endpoint capacity slippage. And as I mentioned, this can be due to things like electrolyte oxidation. Sometimes this can happen because we have higher voltage operation. We might have a non-optimized cathode, like a poor cathode coating, and then also electrolyte choice could enable this to walk along. So using these two metrics gives us a lot of insight. So normally when we plot coulombic efficiency, which is the ratio of discharge to charge, we plot it as coulombic efficiency versus cycle number. So during this test period, about 3 weeks, we see that this goes to about 99.9% coulombic efficiency, and it usually just evens out at this level. And we could see its different contributions, or the different contributions to the coulombic inefficiency, which would be 100 minus the coulombic efficiency. So here's the discharge capacity fade per cycle. So we see the cycle over cycle capacity fade, at least at this rate, at this temperature. And then we could also see that charge endpoint capacity slippage. So the use of this is comparing a few cells. If we see slippage is higher for one cell than the other, this can indicate that it would have the sudden loss in capacity or rollover quicker than the other cell. And then if we see fade is higher for one than the other, we say the fade in normal cell cycling will be higher as well. And we can check this with long-term cycling as well. But NOVONIX UHPC really gives us that confidence really quickly in how the cells will perform. So here's how to compare cells, as I mentioned, using looking at fade. So we see discharge capacity fade is measured by UHPC, and there's 25 cycles. And this red cell, these are both NMC, but the red is NMC 925. So if you asked yourself, should I switch my cell to this NMC 925 as compared to the 811, which is about 83% nickel? You could do UHPC. You see in this case, this NMC 925 has higher discharge capacity fade than the NMC 811. And you would have confidence pretty early, even within 5-10 cycles. So this might be within only in a week. You could know, okay, maybe we shouldn't go with that 925. In this case, just going over the cell build, the same graphite coating was used, so you can really have confidence in this. And you expect that discharge, that fade to be higher, and in fact it was. So it really gives you the confidence, because if you just did a bit of cycling, C/3 cycling and ended here, you wouldn't be like 100% sure that it would be higher fade. But when you do even further long-term cycling, it supports what was found very early on in the UHPC test, that there's more fade from that 925 than the 811. Of course, you may want to still use the 925 if you get higher capacity, or if you can get the material, or it's a lower cost material as well. And then looking at slippage. So in these two cells, so these are two NMC 622 chemistries. So the red, I'm saying it's NMC 2, the black NMC 1. In this case, the discharge capacity fade was similar for both materials, both the cells made with both materials. You can really see that during long-term testing. It's almost the exact same fade. But we do see that the charge endpoint capacity slippage is higher for this red NMC 622 than for the black one. So this would suggest this will probably roll over quicker than the NMC 622 due to some of those reasons that I mentioned before. And you can see this is the case. So the rollover occurs after 2,000 cycles. You see more quicker rollover from the red cell than for the black cell. So this method of determining when, or comparing when rollover will occur, it's an excellent way of using UHPC. You cannot predict from these normal cell metrics when that rollover will occur, but using UHPC will give you some good evidence comparing cells and when they would roll over. So now I'll talk a bit about rate capability and what kind of tests we do for rate capability. So this is our destructive rate capability test, or rate mapping. So first here I'm showing current versus cycle number for the cell. Again, this is the test cell we were talking about, the NMC 811 graphite. And we see that the charge current is shown in black, and that charge current is consistent within this map. So it's a C/20 charge current, and the discharge rate changes. So we see -4 amps for this 4 amp hour cell. So 4 amps would be a 4C rate. 3C, so it starts at C/20, the C/10, C/5, C/2, 1C, 2C, 3C, 4C. In between those higher rate steps, we do a slower rate step. So C/20 discharge here, and then go back to 2C, then C/20, 2 C/20s, then 3C, 2 C/20s, and then 4C. And then we see the resultant normalized discharge capacity. So in this way, we see that there's some loss due to the kinetics of the cell. So this has about 50% discharge capacity retention at 4C rate for this build. This is not a special build for high rate or anything. It's just showing that 4C rate here. So we can do the same for the charge rate map, where the discharge rate stays the same, and then we vary the charge rate. So this is going up all the way to 4C charge. Now, an important thing to see in between these 1C, 2C, 3C, 4C steps, you see that there's loss in capacity in these slower cycles, these C/20 cycles. So this indicates that there's potentially, if we took apart the cell, which we do often, we'd expect to see lithium plating for these cells. This is a loss of capacity during this testing. So this is why it's a destructive test. These cells can't go on to UHPC testing or long-term testing. They'd just be discarded. So how to use this to compare cells? So here are two different types of cells. So they're both NMC 811 cells. We have a formulation of 9642. So this is NMC 811 to Super P to PVDF. We were interested in looking at a higher active amount. So in this way, it would expect to have higher energy density, this cell. So this is going from 96 to 98.54 NMC, 0.4 Super P. There's some CNTs in there and a little less PVDF, half the amount of PVDF. It is calendared to a little higher amount, but this ends up being approximately the same porosity as the initial one because we're losing some of that lower density inactive materials. So again, the same graphite coating was used for both these cells, the red and the black. Remember, the red is the higher active percentage material, so we want to evaluate that. So important, the long-term cycling looked fine at Super 3, so it's important to look at the rate capability. If we see at 1C, 2C, 3C, it's approximately the same losses in discharge capacity. The baseline material is a little bit better rate capability than the higher active. So we conclude that if we are building an energy cell, it should be fine to use this higher active amount, this red cell, this higher active amount than the baseline, if we are seeking out to evaluate a higher energy design. So I'll go into a couple or three special considerations when looking at cell testing. One of them is stack pressure. So stack pressure, normally for our synthetic graphite cells, we use stack pressure of 10 psi, and that cycles well. We notice that for alloy cells with alloy anodes, including silicon type materials, they cycle better at a higher stack pressure. So this is showing that. So we have 10 psi in black. This is normalized discharge capacity versus cycle number. This is C/3 cycling. And then we have in red 30 psi, in blue 60 psi. So our standard is to have our stack pressure as higher, up to 60 psi, especially when we're looking at formulations of up to 50% silicon carbon, 50% graphite as the active material in the anode. It's important to have higher stack pressures, such as 60 psi. If we're lower, maybe 7%, 10% silicon carbon, we might get away with 30 psi cycling. So it's best practice when we are cycling silicon-based anodes to cells with silicon-based anodes to have that higher stack pressure. A really important consideration for cycling is voltage range selection. So here are a few examples. Here's in black is only the discharge curve for C/3 cycling of NMC 811 graphite 1 amp hour stack pouch cell. And we see that at the end of discharge, there's a sudden drop off in the voltage. And so we know we won't get much capacity past a lower cutoff voltage of 2.8 volts. However, for silicon-containing systems, because of the voltage curve of silicon itself, we see that there's more of a sloping profile at the end of discharge, and there's more capacity that can be obtained between this 2.8 voltage, 2.8 volts, and 2.5 volts. So our standard practice is to discharge all the way to 2.5 volts for silicon-containing cells. Of course, unless you want to evaluate a lower depth of discharge. But a full DOD, we would say that's going to 2.5 volts. So other general guidelines along these lines, for upper cutoff voltage, I hinted at this a little bit before. For full cells, for mid-nickel, NMC 631, NMC 622, we're looking at an upper cutoff voltage of 4.3 volts. Because of some structural transitions of higher nickel. So this includes nickel or NMC 811, which is about 83% nickel. Some materials 88%, 90%. Here's NMC 925, which is 92.5% nickel. We know that structural transitions mean that we have to limit that upper cutoff voltage usually. So we're looking at an upper cutoff voltage of around 4.2 volts for cycling. For LFP, around 3.65 volts. There's no more capacity after that. For LMNO, we're looking between 4.8 and 5 volts, and we get better cycling when we're at lower voltages, 4.8, 4.9. That's due to less manganese dissolution at that higher voltage. For sodium-ion battery materials, one example is for the layered oxide, the nickel, iron, manganese containing, like the 111 sodium, nickel, iron, manganese oxide. So those materials cycle best at 3.8. So they can be cycled at upper cutoff voltage 3.8, 3.9. Some of the newer ones may be able to cycle to 4.0, and they're getting better as more development is made. But if you want good cycling of those materials, you get much longer cycling at 3.8 volts. So another special consideration for cell testing is temperature control. So here's showing the discharge in long-term cycling. This is 1C cycling. So at room temperature, we see a lot of wobbly because there's a lot of temperature variation. At room temperature, not a lot. This is HVAC controlled, so it's not too much, but we see some variation. And this isn't too much of a concern because if we're comparing one cell to the next, and the cells are sitting next to each other, they'll experience the same temperature variation and the same conclusions can be drawn. If we do put that cell, these same cells, we just put in a temperature chamber controlled to plus or minus 0.1 degrees Celsius, we do see a lot of smoothing of that data. So if you do want a lot smoother data, we'd put that in the temperature chamber for long-term cycling. You can see fade is a little higher. Room temperature might have been was likely to be lower temperature than 25 degrees. So that's where you see the fade is a little bit more at 25 degrees. So our standard precision usually so we're long-term testing. Room temperature can be fine. If you want smoother data, use a temperature chamber. And then for UHPC testing, because we're looking at the difference between discharge and charge capacities, there can be no variation between one and the next. We need very high precision and accuracy mostly precision to match the high precision and accuracy of the UHPC cyclers. So we put those in temperature chambers that are controlled to plus or minus 0.1 degrees. So just to summarize the discussion for today, so prototype cells at NOVONIX start with making really high quality cells, and that was discussed previously in a few webinars. And if you want to view those, they're on our YouTube channel. So those start with the materials being mixed in a planetary mixer, coated with control and precision in a slot die coater, and constructing the cells with quality standards. Once we make those cells and they're filled, we do standard formation so we can compare one set of cells to the next. And this gives important cell metrics. One is the first cycle efficiency. Another is ACR. That voltage drop at top of charge is a really important metric, as can be the formation gas volume. And these are especially the case when a lot of these when comparing different electrolyte systems. Using NOVONIX UHPC gives an indication of cell lifetime in a relatively short period of time. If we look at the discharge capacity fade, we can quickly predict what the discharge capacity fade will look like during cycling. And then if we look at the charge endpoint capacity slippage, this is a great metric to see comparisons and to understand when that cell would experience rollover. And then long-term cycling can verify the findings in UHPC and then also can be used alone in testing. And as I said, it's important to look at the what current and what temperature is used which when doing this long-term cycling. Again, 1C at room temperature or 25 degrees might be good to show impedance-based fade, whereas like a higher temperature like 40 degrees at C/3 might be better for like a time-based fade to see more degradation at that little bit of an elevated temperature. And then we use rate capability testing. This is interesting if you are looking at testing different conductors, different compression densities, different formulations. It's great to test that to evaluate the kinetics of your cell. And this is done through that discharge and charge rate map, which is a destructive test. And it evaluates the limits, the rate limits of that cell. So special considerations must be made. So stack pressure is an important one, especially dealing with silicon systems. Voltage range selection is important in testing all cells. And also temperature control is very important as well. So that's it for today. We also do a lot of other testing other than this. So that's something that will be discussed in an expected future webinar as well. So keep your eyes open for that.
Great, thanks, Andrew.
You.
Jump into Q&A here. How did you determine all of your set points for cell building, and how do you adjust them based on new materials?
Yeah, so we have a lot of background. A lot of us came from different battery labs and understood different materials. So if you mean like set points like voltage ranges or NMC, LFP, all the different materials, we have a lot of experience testing those. And then we also have a lot of experience with looking in the industry about N/P ratios, about considerations in building the cell, overhang of the anode, for instance. So there's been a lot of background work, not only done at work now, but also in our training that give us these set points and these suggested values of how we test our cells, how the cells are made, what the electrolyte fill factor is. So there's a lot of considerations that go on the background when we do test cells. And then this is done over and over again. So we learn through different testing too what works better. So that helps us control our set points in both of our cell building and our mixing and our cell testing.
Great, thanks. Just this question's in reference to slide 24. You might want to refer back to that. But there's the two cathodes exhibit different slippage, however, a similar trend. So do you judge which one is better just by the magnitude of the slippage, that the red one is worse? And can you expect there will be a rollover based on this slippage, or can you expect when to see this rollover of capacity?
So yeah, so you can't, we wouldn't, they're both leveling out, but we definitely look at the magnitude of the slippage, and I could reference the graph here. So the charge endpoint capacity slippage is the difference between the end of one charge and the next. So if we do look at the magnitude of this, because if that amount is larger, then that means there's more, for example, oxidative processes happening, maybe electrolyte oxidation is happening, and that will result in that rollover. So we do compare that that amount, that magnitude here of one cell compared to the other. So this is important. It's not only the trend. So we would not normalize slippage here when it's shown as slippage per as milliamp hour. And then to predict when the cell would roll over, it's difficult to predict at what point they would roll over. We don't have any equation that would say slippage of 0.5 milliamp hour will roll over at 2000 cycles. So there's other things to take into account. That could be the electrolyte volume, that it could be many different things, because we don't always know without further analysis what processes are happening that are causing the slippage. It could be many different things. So the main use of this slippage metric is to compare one cell to another, and this is exactly showing that. And then when you do a lot of this kind of testing and you do similar cells, you can have a much larger comparison. So you can see if you had 10 cells and then your new cell or your new cathode materials within that cell had lower slippage, you can be really excited early on, because the prediction would be that you would have slippage, that you'd have that rollover much later on. So that's kind of a way to compare one to the other.
Thank you.
And maybe I'll just layer on a little bit of extra information to Andrew's answer there, and kind of put another shameless plug out for one of our other webinars where we go over different applications of UHPC, specifically trying to predict lifetime with some of these metrics. Of course, it's very hard to predict lifetime if you don't know exactly which processes are taking place, what type of actual reactions happening. But UHPC metrics have been shown to provide really valuable layers to machine learning lifetime prediction models. So layering on this extra information about electrochemical stability can really lock in really accurate lifetime prediction models, because there's a lot of different considerations, different failure mechanisms, different pieces of metadata that are really important to what ultimately kills a cell. And this is some really good quantitative data that's otherwise invisible on other cyclers, which is probably leading into the next question that I see.
Yes, why can't we calculate slippage using regular cyclers? And what kind of error should we expect when calculating slippage using regular cyclers versus using UHPC?
Andrew, if you don't mind, I can take that one as well.
Sure.
Yeah, and another shameless plug for our last webinar that we did with UHPC, which was called Inside High Precision. And really, this comes down to the accuracy of a system. But the accuracy is the ability to measure how close you can measure to the exact current that's going through your cell. Every charge-discharge cycler has an inherent bias, channel to channel, it varies, and within charge and discharge. So if your charge is always slightly overcounting and your discharge is slightly undercounting, then you're always going to have a bias towards a much higher slippage. And if the opposite's true, you may even be counting a negative slippage. And ultimately, you need a accuracy that is basically much better than the order of magnitude of these reactions happening. You need your resolution, your accuracy and precision to be much better than the rate at what's happening. If the rate at what's happening is within the noise, you'll never be able to measure it. And in these cases, in modern batteries, the rates that these mechanisms happen at are tiny. They're at ppm levels. So you really do need UHPC. Otherwise, you can calculate slippage, but it's not really going to mean anything. Channel to channel, the noise is going to be, and the inaccuracy will be much bigger than differences cell to cell or chemistry to chemistry.
Thanks, Stephen. Next question, are there recommended viscosity control specs for large batch coating, and do stack pressure requirements differ between single layer and multi-layer cells?
Yeah, so our standard for slot die coating is between 4,000 and 6,000 centipoise. So as I mentioned, we usually start above that. So we just know from practice, if we're mixing a graphite mix, for instance, we might start at 50% solids. And then after that stirring is complete, the mixing is complete, we then take viscosity measurements, and this is using a Brookfield viscometer. And we take our viscosity measurements, and then we change, we keep on adding, for instance, in the graphite case, we keep on adding water until we reach that between 4,000 and 6,000 centipoise. So that's our target viscosity normally for graphite and NMC coatings. In some cases, since that Brookfield viscosity measurement is done at a certain shear rate, and if the material is very shear thinning, we could see cases like this happen sometimes with LFP electrodes, that when they're mixed, we have a target viscosity measurement of 4,000, 6,000 centipoise. Then we bring it to the slot die coater, and it's experiencing so much shear thinning that there's issues maintaining a stable coat weight, and there's some slurry losses as well. So in those cases, we might need to go with even higher solids and have a higher viscosity from that Brookfield viscometer. That's what's because of what we see at the slot decoder. So there's a few things to take into account. And then the next question about stack pressure of multi-layer pouch cells versus single layer pouch. We did, and I mentioned this last webinar on different cell types. So we see that for multi-layer pouch or normal graphite NMC cells, we have a stack pressure of 10 psi. For our single layer pouch, we do see some indication of strange, kind of like strange formation if we're normally at 10 psi. So it seems, so we have success in better formation if we go to higher stack pressure. So it's really pushing out those formation bubbles, which can cause problems within the single layer stack since it's just one unit stack. So our standard is usually 30 or 60 psi for testing in the single layer pouch. And then that resolves the issue of having kind of strange formation. And then if we take apart the cell, you see plating if we are only at lower stack pressures.
Thank you, Andrew. And that brings us to time. So I'll just say a few words before we close out here. Thanks to everyone who joined us today and who shared your questions. We hope you found this session helpful and informative. As a reminder, we'll be sending a link to the recording tomorrow. If you're interested in exploring this topic further, we also encourage you to check out our previous R&D webinar where Andrew discussed NOVONIX's approach to electrode coating and how our R&D services can support your work in developing new battery technologies. We'll include a link to that recording as well in the email. To stay up to date on future webinars, research, and services, you can also follow us on LinkedIn at NOVONIX. On behalf of the entire NOVONIX team, thanks again for spending your time with us today. If you'd like to discuss how our R&D services can support your work, please reach out through our website at novonixgroup.com. Have a wonderful day.